Now the units of activity. Okay. See, here the units of activity are two. On behalf of the name of scientist Becquerel, as well as on behalf of the name of scientist Madame Curie, these two units are there. So, one Becquerel means one disintegration per second. So, when activity of any element we say that is one Becquerel, it implies that from that particular element, one disintegration takes place per second. And Curie, that is the large unit. One Curie, that is 3.7 into 10 raised to 10 disintegration per second. It implies that from the element when 3.7 into 10 raised to 10 disintegration takes place per second, then we can say its activity that is 1 Curie. Okay, so we can write the relationship between Curie and Becquerel as 1 Curie, that is 3.7 into 10 raised to minus 10 Becquerel. And Curie, that is large unit. Therefore, in practice, we use millicurie, that is 10 raised to minus 3 curie, as well as microcurie, that is equal to 10 raised to minus 6 curie. These units we use in practice. Clear to all of you? Half-life. Half-life of the element means the time interval during which the number of undecayed nuclei in the element becomes exactly half than the initial number of undecayed nuclei. That time interval is called half-life, and it is represented by T1 by 2. It implies that as per definition we can write at time t equal to capital T 1 by 2 means at time t equal to half-life time, the number of undecayed nuclei that becomes n0 by 2. So now we have the equation n equal to n0 e raised to minus lambda t. In this equation, substitute time t, that is equal to half-life time t1 by 2. And at that time, the number of undecayed nuclei n, that becomes n0 by 2. So from both the side, n0 cancelled. So 1 by 2, that is equal to e raised to minus lambda t1 by 2. So 2, that is equal to e raised to plus lambda t1 by 2. Now take log at the base of e on both the side. So log at the base of e of 2, we can write that is the natural log as ln 2 also. So on right hand side, we'll get lambda into t1 by 2 log at the base of e of e. So this will be 1. So lambda t1 by 2, that is ln 2. Now convert this ln 2 into 10 base log. So here multiplication factor, that is 2.303 into log 2. So lambda t1 by 2, that is equal to 2.303 and log 2, that is 0.3010. But 2.303 and into 0.3010, that will give you 0.693. Take lambda on right hand side, so we can write the equation for the half-life time, that is t1 by 2 equal to 0.693 upon lambda. Clear to all of you? Mean life. Now mean life of any element, that is the summation of the lives of all nuclei divided by total number of nuclei. That is the mean or average life. Now suppose here at time t equal to 0, number of nuclei, that is N0, and at time t equal to t, number of nuclei, that is N. Now in time t plus dt, suppose dn number of nuclei disintegrates. In short, we can say in time dt, dn number of nuclei disintegrates. Then dn nuclei have the lifetime t. That is total life of dn nuclei. So that is t into dn. Okay. Now total life of N0 nuclei. So integrate this equation 0 to N0 TDN. And now mean life, that is represented as tau, that is equal to, now see here in definition, the sum of the lives of all nuclei. So that is integration 0 to N0 TDN upon total number of nuclei N0. But now we have equation n equal to N0 e raised to minus lambda t. So if we differentiate this one, dn by dt, that is minus lambda N0 e raised to minus lambda t. So minus dn by dt, that is lambda N0 e raised to minus lambda t. Okay. Now here we have the equation tau, that is equal to integration 0 to N0 t into dn. But now from this particular equation, we can write dn, that is equal to minus lambda N0 e raised to minus lambda t, and take this dt on right hand side. So t into minus lambda N0 e raised to minus lambda t dt upon N0 as it is. Now in integration, you do this thing when you change the limit, then sign will be changed. So now 0 to N0, that limit is changed from N0 to 0, lambda t N0 e raised to minus lambda t dt. But now we have to change this particular limit in terms of time. So N0, that is the number of nuclei at time t equal to 0. So now see in this integration, here the lower limit is taken as 0. And the number of undecayed nuclei will be 0 after how much time? We don't know. After infinite time. So upper limit is infinite. So here when the integration, that is of t with respect to dt, so limits are also changed for time t. Now N0 cancelled. So tau, that is lambda integration 0 to infinite t e raised to minus lambda t dt. Now no need to solve this one. Answer of this one, that is 1 upon lambda. So tau, that is equal to 1 upon lambda. Clear to all of you? Again, mean life. The time interval in which the number of undecayed nuclei becomes 1 upon e times the initial number of nuclei. That time interval is called mean lifetime. Now see, here we can write at time t equal to tau. That is the mean lifetime. The number of undecayed nuclei, and that becomes 1 upon e times the initial number of nuclei, means n equal to N0 by e. Now we have equation n equal to N0 e raised to minus lambda t. In this one, substitute t equal to tau. And at that time, your n, that is N0 by e. N0 cancelled. So we can write here on left hand side 1 upon e, that is e raised to minus 1, that is e raised to minus lambda tau. So lambda tau that is equal to 1. Here compare the power on both the side. So tau that is 1 upon lambda. Very simple equation. Now when tau that is 1 upon lambda and half-life t1 by 2 that is 0.693 upon lambda. So here we can write lambda that is 0.693 upon t1 by 2. Substitute this particular value of lambda here. So we can write tau that is equal to t1 by 2 upon 0.693. 1 upon 0.693, that will be 1.44. So we can write a tau that is equal to 1.44 t1 by 2. Or we can write t1 by 2 that is equal to 0.693 into tau. So the relationship between mean life and half-life time, that is this one. Clear to all of you? Example 13.4. The half-life of uranium-92-238 undergoing alpha decay is 4.5 into 10 raised to 9 years. What is the activity of 1 gram sample of uranium-92-238? Now the sample is uranium-92-238, half-life that is 4.5 into 10 raised to 9 year. So half-life that is 4.5 into 10 raised to 9, and 1 year that is 3.16 into 10 raised to 7 seconds. So this much total second. Now activity that is R equal to lambda into N. But lambda that is 0.693 upon T1 by 2 into N. But here we want to find the activity of 1 gram sample. So first of all, we have to find the number of nuclei in 1 gram sample. So here if we take uranium 238 gram equal to its atomic mass in gram, then that is 1 mole substance. The number of nuclei that is 6.02 into 10 raised to 23. Therefore, in 1 gram, how many? So n equal to 6.02 into 10 raised to 23 upon 238. Now in this equation of activity R, substitute value of half-life and n. So 0.693 into 6.02 into 10 raised to 23 upon half-life 4.5 into 10 raised to 9, 3.16 into 10 raised to 7, and 238 as it is. Clear? Now solve this one. You will get the answer of activity of 1 gram substance. Example 13.5. Tritium has a half-life of 12.5 years undergoing beta decay. What fraction of the sample of pure tritium will remain undecayed after 25 years? Now see here, T1 by 2 that is given to you 12.5 years. Okay. Now see, at time T equal to 0, number of undecayed nuclei that is N0 means 100% is there. So after time equal to half-life, number of undecayed nuclei becomes exactly half, so it becomes N0 by 2. So that becomes 50%. Clear? Now half-life that is 12.5 years. So again, if we take here another half-life time, so 2T1 by 2. So total time interval that becomes 25 years. 12.5 plus 12.5. So now the again number of undecayed nuclei becomes half than this one. So half then this one, that is N0 by 4. So that is 25%. It implies that after 25 years, 1/4 part of the tritium will be undecayed. Or in other words, we can say 25% will remain undecayed and 75% will be decayed. Clear to all of you?